Welcome to the fourth chapter of machine design, shafts, gears and bearings. We will see bearings in this session. Bearings are machine elements which are used to support a rotating member, that is a shaft. They transmit the load from a rotating member to a stationary member known as a frame or housing. So there are two members, one is a stationary member and one is a rotating member. Bearings are used to transmit the load from a rotating member to a stationary member, and this stationary member is also known as a housing or a frame. So they permit the relative motion of two members in one or two directions with minimum friction, and also prevent the motion in the direction of the applied load. So these are the function of a bearing. So bearings are basically classified into two categories based on the type of contact they have between the rotating and stationary members. So here we are told that bearing is transmitting a load from a rotating member to a stationary member. So what is the type of contact between the rotating member and stationary member? Based on that, bearings can be classified into two. One is called a sliding contact bearing, and second one is a rolling contact. So basically two types of bearings, so sliding contact bearing and rolling contact bearing. The sliding contact bearings have surface contact and are coming under lower kinematic pair. So this is surface contact. Now we will see about the sliding contact bearing in detail. Sliding contact bearing, also called as journal bearing or sleeve bearing. Journal or sleeve bearing. Among the sliding contact bearing, radial bearings find wide applications in industries, and hence these bearings will be dealt in detail. The radial bearings are also called journal bearings or sleeve bearings. Also called as journal bearings or sleeve bearings. And depending on the extent to which the bearing envelops the journal, now we will see how the bearing looks like. This is a schematic of a radial bearing or journal bearing. This is the outside stationary member called the frame or housing or the shaft. This is the inside rotating member called the journal. And in between the two members we have the lubricant, which will be filling the space between these two members. And depending on the extent to which the bearing envelops the journal, the bearing are classified into three types, mainly full bearings, partial bearing and fitted bearings. So we have seen the rotating member is a journal which is inside a stationary member called the frame or housing, and in between these two we have the lubricant. So now we will classify the types of, now we will see what are the different types of lubrication available. Different types of lubrication are available, and they can be classified as basically, one is hydrodynamic lubrication, hydrostatic lubrication, then we have elasto-hydrodynamic lubrication, then we have boundary lubrication, and finally we have solid film lubrication. These are the different types of lubrications. Now we will see the first one, which is the hydrodynamic lubrication. Hydrodynamic lubrication means that the load carrying surfaces of the bearings are separated by a thick film of lubricant so as to prevent the metal to metal contact. So in hydrodynamic lubricant there is no metal to metal contact, and it is a thick film of lubricant is available between the rotating and stationary member. Thick film of lubricant, and the stability obtained by a hydrodynamic lubrication can be explained by laws of fluid mechanics. It's a simple viscosity laws only. This will be seeing in detail. Hydrodynamic lubrication does not depend upon the introduction of lubricant under pressure, but it does require the existence of a adequate supply at all times. That is, we are not adding the lubricant under pressure like in hydrostatic case we will be seeing later. In hydrodynamic case we are supplying the lubricant but not under the external pressure. Therefore, no introduction of lubricant under pressure. So, the lubricant is present between the journal and the stationary member, but it is not applied, pressure is not applied on that lubricant. The film pressure is created by the moving surface itself, pulling the lubricant into a wedge-shaped zone at a velocity sufficiently high to create the pressure which is necessary to separate the surface against the load. That is, when this is rotating, this itself squeezes the lubricant into a wedge-shaped zone which provides the pressure to the lubricant. And hydrodynamic lubrication are also known as full film lubricant, full film lubrication, or it's also called as fluid lubrication. The main thing is external pressure is not applied on the lubricants, and the pressure is generated by the relative motion between the journal and the stationary member. That is a specialty of hydrodynamic lubrication. These are used when the loads are not much high. Now we will see the next type of lubrication, basically the hydrostatic lubrication. Hydrostatic lubrication is obtained by introducing the lubricant, which may be air or water, into the load bearing area at a pressure which is high enough to separate the surfaces. That is, here we have introduction of lubricant under pressure. Hydrodynamic case, in hydrostatic case, the lubricant is introduced under pressure which is high enough to separate the stationary and the rotating members. Unlike the hydrodynamic lubrication, this kind of lubrication, that is hydrostatic lubrication, does not require motion of one surface relative to another. In hydrodynamic, we saw that relative motion of the two members, the rotating and the stationary rotating members, causes the lubricant to be squeezed into a wedge-shaped zone which gives the necessary pressure to separate the both the surfaces. Here, since external pressure is already available, the two surfaces need not be in relative motion, one can be stationary also. That is, this does not require motion of one surface on another. And the hydrostatic lubrication is slightly complicated in nature. So, in our course on machine design, we will be dealing more with the hydrodynamic lubrication. So, next comes the elasto-hydrodynamic lubrication. Elasto-hydrodynamic lubrication is a phenomena that occurs when a lubricant is introduced between surfaces that are in rolling contact. Surfaces in rolling contacts, mainly in gears or the rolling bearings, gear drives or rolling bearings. The lubrication used there is known as elasto-hydrodynamic lubrication. And since it is a contact kind of a phenomena, we have the Hertzian theory of contact stress is used for explaining the phenomena. Hertzian contact stress is used to define the behavior of elasto-hydrodynamic lubrication. Now comes the fourth one, mainly the boundary lubrication. Sometimes what happens is the insufficient surface area or a drop in velocity or a lessening in the quantity of lubricant or increase in the bearing loads, these may result in the decrease in the viscosity of the fluid, and also it will prevent the buildup of a film which is thick enough for full film lubrication. So, such cases we will not get a full film lubrication. And what happens is when this kind of a thing happens, when the viscosity of the lubricant reduces, only the highest asperities may be separated by the lubricant film. This is called the boundary lubrication. That is, insufficient maybe a drop in velocity, increase in load, increase in temperature, etc. causes decrease in the viscosity of the fluid. In such cases, full film lubrication is not possible. Or in such cases, what we have is boundary lubrication will be the. Actually, when it starts, it will be starting with the hydrodynamic lubrication, and the change from hydrodynamic to boundary lubrication will not be a sudden, but it will be a gradual one. First we have a hydrodynamic lubrication, then we have a mixed hydrodynamic and boundary type lubrication. And as the surface move close together, the boundary type of lubrication becomes predominant. So initially it will be starting with a hydrodynamic lubrication. Gradually it becomes a mixed type of lubrication, that is mixed hydrodynamic boundary type lubrication. And the surface, when the surfaces come close to each other, it becomes boundary lubrication predominates, and finally it takes over the hydrodynamic lubrication, and finally we get a boundary type of lubrication. So that is about the boundary lubrication. It's nothing but a the other extent of hydrodynamic lubrication will be the boundary lubrication. And the last one which we have is a solid film lubrication. When the bearings must be operated at extreme temperatures, a solid film lubricant such as graphite or molybdenum disulfide may be used because the ordinary mineral oils are not satisfactory. So these are the lubricants which takes care of the high temperature. Basically, in the case of high operating temperatures, solid film lubrication may be used. Solid film lubrications are nothing but instead of oil which we use for the hydrodynamic lubrication, we use a solid which is maybe a graphite, or it will be a molybdenum disulfide. This can be used as a lubricant in place of a mineral oils. So these are different types of lubrication that is available. Now we will come to the details of the physics of lubrication, physics of the working principle behind the bearings. Before we go into the details of the working principle, we will see the fundamental principle of viscosity. What is viscosity? When two plates shown here are present, and in between you have a fluid film, and one of the plate is stationary, this plate is stationary, and the other plate is moving with velocity v. In such cases, what happens? The fluid film which is in contact with the plate will be moving in this velocity u, and the fluid film which is in contact with this plate will be at rest. So in between this fluid film is getting a velocity gradient across the thickness h, and due to this shear stress gets developed in the fluid, which is given by the Newton's law of viscosity. Newton's law of viscosity states that when two plates are there having a relative motion of u, and when a fluid is present between the two plates, a velocity gradient gets established in the fluid film, and this velocity gradient causes shear stress to be developed within the fluid film, and the shear stress is given by F by A. It's nothing but mu times du by dy, where du by dy is called the velocity gradient across the thickness. So velocity gradient across thickness. In this case, we can say this as the velocity gradient will be, the topmost layer will have velocity u, the bottommost will have velocity of 0. So gradient will be u minus 0, and the thickness between them is h. So velocity gradient is nothing but u by h. The term mu is called the coefficient of viscosity. It's called coefficient of viscosity of the fluid, or liquid. So we get tau is equal to mu times du by dy, or in the current case we get the shear stress tau is equal to mu times u by h. So this is a fundamental principle which we use for analyzing the working principle of bearings. Suppose now we will consider a case where this is again a stationary member only, but This is a rotating member, rotating shaft, which rotates at an angular velocity of omega. And if it is having a radius r, then what we can write? That is, if this is a shaft which is revolving at an angular velocity of omega and is having a radius of r, and what will be the tangential velocity? The tangential velocity v will be equal to r omega. So here now the velocity u will be replaced by r omega. In that case, the shear stress developed is given by mu times r omega by h. This which is a solid shaft of radius r rotating at an angular velocity of omega. Angular velocity of omega. Then the shear stress developed is given by tau is equal to mu times r omega by h. So that is about the viscosity of fluids. Now we will see about the analysis of bearing. Now these are two views of the bearing. This is a journal and this is the stationary housing, and in between one is called the lubricant. And a small load of W is acting on the journal. Now if the clearance between the two shafts is given by C, then the shear stress we know is given as mu times u by C, where u is the tangential velocity of the journal, C is the radial clearance, and mu is the viscosity, coefficient of viscosity of the lubricant. Now as we have seen earlier, if this shaft is rotating with the angular velocity omega, and if r is the radius of the shaft, the tangential velocity u is given by r into omega, or it can be written as r into 2 pi n by 60, where r is the radius of the shaft, n is the rpm, that is what revolutions per minute of the shaft. So the tangential velocity is given by 2 pi n r into by 60. Therefore the shear stress will be given as mu times u by c. Mu times u is nothing but 2 pi r n by 60 by c. So this will be the shear stress, and the shearing force acting on the lubricant, the shearing force trying to shear the film, F is given as shear stress into area, that is equal to shear stress into the area will be 2 pi r into L. Now the area will be this circumference multiplied by the length. That will be the area of film which is getting sheared. Therefore the shearing force will be tau into 2 pi r L. That can be written as mu by c 2 pi r n by 60 into 2 pi r L. Or we can write the shearing force as 2 pi r whole square into mu n L by 60 c. Here L is the length of the shaft, mu is the coefficient of viscosity, n is the rpm of the shaft, L is the length of the shaft, c is the radial clearance, r is the radius of the shaft. So this is the shearing force. The torque is given by force into radius. Therefore torque due to the lubricant will be given as 4 pi square r cube 4 pi square r cube L mu n by 60 c. This is the torque due to the lubricant. It can be written as 4 pi square r cube L mu n by 60 C. This is a torque due to the viscosity of the lubricant, and the power loss due to the viscosity is given as torque into omega. So that can be calculated from the relation. This is the power loss due to the viscosity. Now, when a small load of W is acting on this shaft, this causes a pressure on the lubricant, which is given by pressure is equal to W by 2RL, where 2RL is the projected area. If the load W is acting, the pressure due to the small load P is given as W by 2RL. This is the pressure due to the small load W acting. So W can be given as 2RL into P. Now the frictional force acting is given by mu times the normal reaction. That's equal to, in place of mu we will put F, where F is the coefficient of friction. It's important here, since dynamic viscosity, because since mu has been used for dynamic viscosity, F will be used for denoting the coefficient of friction. Therefore the frictional force will be given as F times normal reaction. Here the normal reaction is nothing but W. Therefore the frictional force will be given by F times W, and the torque due to this is given as frictional force into radius, that's equal to F into W into R. Therefore torque due to the frictional force is given by F times W is nothing but P into 2RL into R. So that's torque due to friction is given by 2R square L P into F. This is a torque due to the frictional force. And torque due to the viscosity of the fluid is given by 4 pi square R cube L mu n by 60 C. Therefore for condition of equilibrium, the torque due to the viscosity of the lubricant should be equal to the torque due to the frictional force. Therefore equating both of them, that is torque F is equal to torque viscosity, will give the coefficient of friction F as 2 pi square by 60 mu n by P into R by C. The coefficient of friction is given as 2 pi square by 60 mu n by P into R by C. This equation is called Petrov equation. This is important equation as far as bearing is concerned. So we will write once more. Petrov equation can be written as the coefficient of friction F is given by 2 pi square by 60 into mu n by P into R by C. We will define the parameters. N is the RPM of shaft, mu is the dynamic viscosity of the lubricant, P is the pressure due to the small load W, R is the radius of the shaft, C is the radial clearance, F is the coefficient of friction, and mu n by P is called the bearing modulus. Now another term of importance is the Sommerfeld number. Sommerfeld number also called as the bearing characteristic. given as S is equal to R by C whole square into mu n by P 1 by 60. This is the Sommerfeld number or the bearing characteristic, where R by C is called the radial clearance ratio, used both in the Petrov equation as well as the Sommerfeld equation. R by C, the radial clearance ratio, and mu n by P is the bearing modulus. These two terms are of importance for the design of bearings. Now we will see another important parameter in the field of lubrication, that is nothing but the stability of lubrication. While we are discussing about lubrication, we have heard of terms thin film lubrication and thick film lubrication. So till now we were not in a situation to say what is thin film lubrication and what is thick film lubrication. To define that more precisely, we are using this curve between the coefficient of friction and the bearing modulus mu n by P. In this curve, suppose consider to the right side of this red line, what happens? Suppose if you are in this location, if your loading is such that you are at this point, when the temperature increases, what happens? When the temperature increases, the viscosity of the fluid decreases. That is, if F increases, that is, if you are going up this curve, the coefficient of friction increases, or if you are going up in this curve, what happens? When the coefficient of friction increases, the temperature increases. When the temperature increases, the dynamic viscosity of the fluid will reduce. When the dynamic viscosity of fluid reduces, it comes back to this point. That is, when you are starting from a point, and when the coefficient of friction increases, temperature increases and brings down the bearing modulus, and it comes back to the original point. So this kind of lubrication is called the stable lubrication, because when the temperature increases, it automatically comes down to the initial point. So this is called a stable lubrication. And this side of the curve, that is left side of this line, in this side what happens? If you suppose at this point, if you start at this point, when the coefficient of friction increases, that is, you have to come up this curve. When the coefficient of friction increases, what happens? We know temperature increases and dynamic viscosity decreases. But when the dynamic viscosity decreases, it doesn't come back here, because if it has to come back, then that means dynamic viscosity should increase. Since the dynamic viscosity is reducing, it again goes to this curve. So what happens when the coefficient of friction increases? So in this case, what is happening is, the coefficient of friction increases, the temperature increases, dynamic viscosity decreases, and it goes to a higher value of coefficient of friction. Again the temperature will be much higher, dynamic viscosity will still reduce, and it will again go in this curve. So such kind of a lubrication is called a unstable lubrication, because it goes away and away from the initial point and never comes back to the initial point. So this kind of a lubrication is called an unstable lubrication. That is, left side of this line is the unstable lubrication or thin film lubrication, and right side of this line is the thick film lubrication or stable lubrication. Now that is about the sliding contact bearings and the lubrications. Now to have a better understanding, we will try to solve some one or two problems related to the journal bearings. Now we will try to solve one problem. A lightly loaded full journal bearing has journal dia of 50 mm and a bush bore of 50.05 mm and the bush length of 20 mm. If the rotational speed is 1200 rpm and the average viscosity of the liquid lubricant is 0.03 pascal second, the power lost in watt is. Now we will write down what are the parameters given here. The journal diameter is given as 50 mm. Therefore R is equal to 50 by 2 d by 2, that is equal to 25 millimeter or 25 into 10 raised to minus 3 meters. We will try to work in SI units. And the radial clearance, it's given as bush bore is 50.05 mm or the diameter clearance is 0.05 mm. Therefore radial clearance will be 0.05 by 2 mm, that will be equal to 0.025 into 10 power minus 3 meters. Then the length of shaft is given as 20 millimeters. That will be 20 into 10 power minus 3 meters. Then the speed of rotation is given as 1200 rpm. And the dynamic viscosity of the lubricant is given as 0.03 Pascal second. So what is the power loss due to the friction of lubricant viscosity? Now we know that the frictional force, the shear force due to viscosity is given as 2 pi r whole square mu nl by 60 c. Torque is given as 4 pi square r cube into mu nl by 60 c. Therefore power loss will be given as, we have already seen, power loss is equal to T into omega, that is given as 4 pi square r cube by 60 mu nl into omega is nothing but 2 pi n by 60. So this is only substitution. So that is equal to 2 pi r okay, so what this will be equal to, you can just calculate it. So this will be equal to 4 pi square into 0.0 will be 25 into 10 raised to minus 3 whole cube into 0.03 into 1200 into 0.02 by 60 into 0.025 into 10 raised to minus 3 into 2 pi into 1200 by 60. So how much this will be? 4 pi square into 25 into 10 raised to minus 3 whole cube into 0.03 into 1200 into 0.02 divided by 60 into 0.025 into 10 raised to minus 3 into 2 pi into 1200 divided by 60. This will be equal to 37.2 watts. So thus the power loss due to the viscosity of lubricant will be equal to 37.2 watts. So thus we can find out easily the frictional force, the torque due to the frictional viscous force, torque due to the viscous force, and the power loss due to the viscosity of lubricant. This much factors we can easily find out using the following parameters. This question was asked in GATE 2010. So once we know the concept, then we can easily solve this kind of problems. We'll solve one more problem. We'll try to solve one more problem. A journal bearing has shaft dia of 40 mm and length of 40 mm. The shaft is rotating at 20 radians per second and the viscosity of lubricant is 20 millipascal second. The radial clearance available is 0.02 mm. Now then, what is the loss of torque due to the viscosity of lubricant? Now as usual, we'll list down the parameters which are given in this problem. So the journal diameter is given as 40 mm. Therefore radius is equal to 20 mm. It's equal to 20 into 10 power minus 3 meters. Shaft is rotating and the length is given as 40 mm. That's equal to 40 into 10 power minus 3 meters. And the shaft is rotating at a angular velocity of 20 radian per second. Therefore omega directly is given as 20 radians per second. Viscosity of the lubricant mu is given as 20 millipascal second. That's equal to 20 into 10 raised to minus 3 pascal second. Now we have to find what is the loss of torque due to the viscosity of lubricant. So how we can find out? We know that the shear stress is given as mu times u by c, where the tangential velocity u is given by r omega. So this becomes mu times r omega by c. This is the shear stress. Now this is, I'll write as shear stress. Now the shear force F is equal to tau into A, that's equal to mu r omega by c into area is 2 pi r into L. This is the shear force. So we'll write out here. The shear force is given as mu r omega by c into 2 pi r into L. We'll try to retain the angular velocity as such. Now this is the shear force. Therefore the torque will be given as the shear force into radius r, that will be equal to mu r square omega by c into 2 pi r L. This will be the torque loss due to the viscosity of the lubricant. Now that is what is asked here. So we can substitute the values. Mu, the coefficient of the dynamic viscosity mu is given as 20 into 10 power minus 3. The radius of the shaft r is given as 20 into 10 power minus 3, 20 millimeters square, into the angular velocity omega is given as 20 radian per second into 2 pi into the radius is 20 into 10 power minus 3. The length of the shaft is given as 40 millimeters. So 40 into 10 power minus 3 divided by the radial clearance is given as 0.02 millimeter minus 3. So what this will be? 20 into 10 power minus 3 into 20 into 10 power minus 3 square into 20 into 2 pi into 20 into 10 to the minus 3 into 40 into 10 to the minus 3 equal to divided by 0.02 into 10 to the minus 3. This will be equal to 0.04 Newton meter. This is the loss in torque due to the viscosity of the lubricant. Now what will be the power loss due to the viscosity of lubricant? The power loss will be equal to torque into omega, that's equal to 0.04 into omega is 20 radian per second. So that is equal to 0.8 watts. This is the power loss due to the viscosity of the lubricant, and this is the torque loss due to viscosity of lubricant. So again it's the same thing. Once we know all the concepts, we can easily substitute the values in the formula and we can find out the answer. We need not by heart any equation. We can, given any problem like this, we can derive what will be the formula we have to use. So in this formula we have retained the angular velocity as such, but in the derivation we have used converted the angular velocity in terms of the RPM of the shaft. Depending on the problem, you can derive the equations and substitute the values and get the answer. So we'll try to solve one more problem on journal bearings. A natural feed journal bearing of diameter 50 millimeter and length 50 millimeter operating at 20 revolutions per second carries a load of 2 kilonewtons. The lubricant used has a viscosity of 20 millipascal second and the radial clearance is 50 microns. What will be the Sommerfeld rating for the bearing? Now, as usual, we will list down what are the parameters given here. The diameter of the shaft is given as 50 millimeter. Therefore, R is equal to 25 into 10 raised to minus 3 meters. The length of the shaft is given as 50 millimeters. That is equal to 50 into 10 power minus 3 meters. The operating speed omega is given as 20 revolutions per second. So we can write as 20 revolutions per second. The load carried is capital W is equal to 2 kilonewtons or 2000 newtons. The lubricant used has a viscosity, dynamic viscosity of the lubricant is given as 20 millipascal second, 20 into 10 raised to minus 3 pascal second. The radial clearance is given as C is given as 50 microns or 15 into 10 raised to minus 6 meters. What is the Sommerfeld number? S we know is given as R by C whole square into mu n by P into 1 by 60. Please keep in mind that the n used here is the RPM of the shaft, or rotations per minute of the shaft. But in this problem, the speed is given as revolutions per second. So we have to find n is equal to how many, if this many revolutions per second is there, what is the revolutions per minute? So it will be into 60. So that will be equal to 20 into 60 revolutions per minute, or 1200 RPM. So here R is given, the radius of shaft is 25 millimeters, C is 50 microns, mu is 20 into 10 to the minus 3, N is 1200, P, the pressure due to the minimum load W is given as P is equal to W by 2RL, where 2RL is the projected area of the shaft. So this is given as 2000 newtons divided by 2 into 25 into 10 raised to minus 3 into L, that is 15 into 10 raised to minus 3. This will be P. Now substituting all values in this equation, S is equal to R by C, that is 25 into 10 raised to minus 3, that is radius, divided by C is 15 into 10 power minus 6 whole square into mu is 20 into 10 power minus 3 into N is 1200 divided by P. P is nothing but 2000 divided by 2 into 25 into 10 raised to minus 3 into 50 into 10 raised to minus 3 into 1 by 60. Now what will be this? So 25 into 10 raised to minus 3 divided by 15 into 10 raised to minus 6 whole square divided by 60 is equal to into 20 into 10 raised to minus 3 into 1200 divided by 2000 divided by 2 and 25 into 50 into 10 raised to minus 6 will be equal to 0.125. Therefore, the Sommerfeld number will be equal to 0.125 for this kind of a bearing. So this is also another example of how we can solve the problems knowing the concepts. So again, there is no necessity to by heart any equations. Just list down all the, once we are given such kind of a problem, and this was asked in GATE 2007. This is only a substitution of variables. So first thing we have to do, if you get any problem on bearing, is to list out what are the parameters given in the question. Then what they have asked, Sommerfeld number. So write down what is the equation of Sommerfeld number and see whether you have all the variables with you. Like if some variables you are not getting, it may be in terms of other parameters. Like in this equation, N is the RPM or revolutions per minute of the shaft, but you are given revolution per second of the shaft. So you have to convert it accordingly into revolutions per minute and use it. And P, which is the pressure due to the load W. Since load is given and the projected area is given, you can find what is the pressure. So this is only a substitution of variables into the formula. So thus this kind of problems can be easily solved once you know all the concepts related to the bearings. And keep in mind that don't make mistake with the units. It would be better to use the SI units so that it will be a consistency of units can be easily maintained if you have a SI, if you are following a SI system. So convert all the distance lengths into millimeters into meters, speed in RPM, load in newtons, pressure in Newton per meter square, and viscosity in Pascal second, and any length unit should be in meters. Once you make sure, then we can find out any problem can be solved by substituting of the variables. And once you make everything in the same units, we can make sure that we don't make any mistakes with the units. So thus this kind of problem can be easily solved knowing the concepts. Having seen so much about the sliding bearings or the journal bearings or the radial bearings or sleeve bearings. Now we will come to the next type of bearing, which is nothing but the rolling contact bearings. Rolling contact bearings mainly are of two types. First is the ball bearing and next is the roller bearing. For the rolling contact bearing, the most important aspect is the life of the bearing or the load life relationship. For bearing, load life relationship is the most important relation for rolling contact bearings. The load life relation is nothing but given the load, what will be the life of the bearing. Life of the bearing L10 is given as C by P whole cube for ball bearings and is given as C by P raised to 10 by 3 for roller. So what is L10? L10 is nothing but the life in millions of revolution, 90% of a group of bearings, will complete before any evidence of fatigue. That is, if you take a group of bearings, 90% of the group of bearings will complete L10 millions of revolution before having any evidence of fatigue. That is nothing but the life of bearings with a 90% of confidence. So we can say that this is the life of bearing with a 90% of confidence. In this relation, C is nothing but the dynamic load carrying capacity and P is the equivalent dynamic load for the bearing. Now the life in millions of revolution is very difficult to interpret, because we know the life in hours means we can easily find out, it's more easy to visualize that. So life of hours can be obtained from the life in millions of revolution by this relation. L10 is equal to 60 N LH divided by 10 power 6, where LH is the bearing life in hours and N is the speed of rotation and L10 is the life in millions of revolution. So once the life in millions of revolution is known, we can find what is the life in hours using this relation. Now we will try to solve a simple problem which is given here. The dynamic load carrying capacity of a 6306 bearing is 22 kilonewtons. Then what is the maximum radial load it can sustain to operate at 600 revolutions per minute for 2000 hours? Now what should be the radial load, maximum radial load, such that it can operate at 600 revolution per minute for 2000 hours. Now we will list down what are the parameters given here. The dynamic load carrying capacity C is given as 22,000 newtons or 22 kilonewtons, and L, now L10 we have to find out. L10 is nothing but 60 N LH by 10 power 6, that's equal to, what is N here? N is the RPM, that is 600 revolutions per minute, and LH, that life in hours is 2000 hours. Then what will be the life in millions of revolution? This will be equal to 60 into 600 into 2000 by 10 power 6. 60 into 600 into 2000 divided by 10 power 6, that's equal to 72 million revolutions. So L10 is equal to 72. If L10 is 72 and C is, now L10 is 72 and C is 22,000 newtons, so what will be P? This 6303 bearing is nothing but a ball bearing. So we can say that L10 for this bearing is equal to C by P whole cube. Therefore C is known, L10 is known, we have to find what is P. So we can write P is equal to C by L10 whole power 1 by 3, that's equal to 22,000 divided by 72 raised to 1 by 3, or cube root of 72. 22,000 divided by cube root of 72 will be equal to 5288 newtons. So this is the equivalent dynamic load, or this is the maximum radial load it can sustain to operate at 600 revolution per minute for 2000 hours. Thus we can find out using the simple relations, load life relationship, we can solve the problem and find out the load carrying capacity and the dynamic load which can be carried by a rolling contact bearing, maybe a ball bearing or a roller bearing. So with this we come to the end of this chapter on bearings. We have covered the sliding contact bearings and rolling contact bearings. Sliding contact bearings mainly we have seen the journal bearings. Different type of lubrication also we have seen. The hydrostatic lubrication, hydrodynamic lubrication, elasto-hydrodynamic lubrication, boundary lubrication and film lubrication. Then we have seen the viscosity of lubricants, how it is derived by using Newton's laws of viscosity. Then we have seen about the Petrov equation. Then we have seen what is the bearing modulus, what is Sommerfeld number for a bearing. Then we have solved some 3-4 problems also. Then we came to rolling contact bearings. Here we have seen the load life relationship and how to calculate the dynamic load carrying capacity and the equivalent dynamic load, and how to find out the life in millions of revolution, also how to find the life in hours for a bearing. So with this we come to the end of this module on bearings. Thank you.